Good afternoon to everybody. So today our topic of discussion is function. The question comes, what is a function? Function is a special type of relation. What is the meaning? What is here special type? Suppose let A and B are two sets, then a function f from A to B is defined as follows. Here f is a relation such that every element of set A is related to one and unique element of B. Here we have to give an importance to the unique element. That means a function is a relation. Basically, suppose 1 is related to A, 2 is related to B, and 3 is not related to any element of B, then it is not a function, because I have told that every element of A must be related. Suppose 1, 2, A, B, C. 1 related to A, 2 related to B, 2 related to C. This is a relation, but it cannot be a function because the element 2 is related to two elements, B and C. So, it is not a function. If one related to A, 2 related to B, and there is another extra element C of set B which is not related to any element of A, then it is a function. Three related to B, 2 related to A, and 1 related to A. This is also a function. So the restrictions, every element of A must be related to one and unique element of B. This restriction is not applicable to the elements of set B. There may be some elements in set B which are not related to any element of A. Also there are some elements in set B which are related to more than one element of set A. Suppose we will consider another example. One related to A, 2 related to B, 3 related to C. Here A is called domain of F, B is called codomain of F, or in some of the books you will find that another terminology, target of F. This is also told as target. Here in this case, or here F1 equals to A, F2 equals to B, F3 equal to C. That implies 1 is preimage of A and A is preimage of 1. That means in relation we are taking A as set, domain set, and B as codomain set. Here we can also tell A as preimage set, B as image set. It can be also told as image set, pre-image set. In this example, f1 equals to a, let us consider this example, f1 equals to a, f2 equals to b. C is not related to any element under the function f. Here range set is a and b, but not whole the set. This whole set b is called codomain set, and the elements of b which are related to the elements of a, they are treated as the elements of range set. Or we can write 1fa, 2fb like this. So we have already defined what is domain, what is codomain, what are the pre-image, what are the images. A is called image of 1. Then we will come to types of functions. First is 1-1 function or injective function. This terminology function is also called as graph of A to B, or also transformation of A to B, or transform of A to B, like this, or mapping. In some of the books you will find the terminology, instead of function it is mapping. That is, F maps A into B, injective function. We are all acquainted with injections. A person will be given one injection bottle. It cannot be distributed among other persons. So that means a person is corresponding to one bottle of injection. Similarly, if there is a 1-1 correspondence between elements of A and B, like this function is 1-1 or injective. Also this is also an injective function. That means f from A to B is an injective function if there exists a 1-1 correspondence between the elements of A and B. There is one condition, mathematical condition for 1-1 function. What is that? For x1, x2 belongs to A, if fx1 equals to fx2 implies x1 equals to x2. If this condition is satisfied, your assumption condition is fx1 equal to fx2, and we have to prove that x1 equals to x2, then the function is 1-1. Or in negative sense, you can prove like this: x1 not equal to x2 implies fx1 is not equal to fx2. We can prove like this also. Let us see with an example. Let us consider a linear function. You are all acquainted with linear function. That means the function whose degree is 1. Degree means highest power of the variable present in the function. fx equals to 2x plus 3, where f is a function from R to R, set of real numbers to real numbers. Let x1, x2 belongs to R, and fx1 equals to fx2. That implies 2x1 plus 3 equals to 2x2 plus 3. That implies 2x1 equals to 2x2. By cancellation law, that implies x1 equals to x2. We have assumed that fx1 equals to fx2, and we reached at the point x1 equals to x2. That means f is 1-1 or injective. Then comes our next function is onto function or surjective function. That means a function f from a to b is an onto function or surjective function if every element of set B has at least one preimage in the domain set. Like this. Here A has two preimages, 1 and 2, B has one image, but in this case, one related to A, 2 related to B, but C is not related to any elements. That means C has no preimage. Then this function is not an onto function. That means the condition is every element of the range set, codomain set must have at least one preimage in the domain set. F from A to B is an onto function if every element of set B has at least one preimage in the domain set. Here in this example, A having elements 1, 2, 3. So f of A equals to f1, f2, f3. Here 1 related to A means f of 1 equals to A, 2 related to A means f of 2 equals to A, 3 related to B means f of 3 equals to B. That implies f of A has elements A, B. What is? That is our set B. That means f of A equals to B is the condition for a function to be an onto function. Next, first we have discussed one function, then onto function, then combination of both of these, one and onto, or its another name is bijective function. If f is a function from A to B and f is both 1 and onto, then f is a bijective function. A having elements 1, 2, 3, B having elements A, B, C. Here the function is clearly 1 because there is a 1 correspondence between the elements of A and B, and the function is onto because every element of set B has a preimage in the domain set A. So this function is a bijective function. Then inverse of a function. Let f is a function from A to B, then inverse function f is defined. There is a restriction only when f is bijective. If the parent function f is bijective 1, then there must be the existence of inverse function. Now the question comes, you may ask the question, why the function f must be bijective? Suppose like this. Here A to B is the function f and B to A will be f inverse. Here domain of f inverse will be set B. From the definition function we know that one element of the domain set must be related with unique element of set, range set or codomain set. Here B is related to two elements 2 and 3. Therefore, F inverse will not exist. That will contradict our basic definition of the function. That means one element of the domain set related to two elements. In this case also, this is a function. One related to A, two related to B. C is there having no preimages. When we will consider our F inverse, then in the domain set there is an element C lying vacant which is not related to any element of the set A. That means it has no image. Therefore, it is not F inverse. That is for existence of F inverse, the parent function F must be bijective 1, that is both 1 1 and 1 2. So naturally F inverse is a function from B to A. Suppose in this case F having elements ordered pairs 1A, 2B, 3C. So naturally F inverse will be just reverse the ordered pairs A1, B2, C3. Also we can write 1 F inverse A, 2 F inverse B, 3 F inverse C like this. So all these are graphical representation of functions. Next comes our composite function. Composite function. Suppose here there are three sets will be involved. F is a function from A to B, G is a function from B to C. Graphically we can write like this. A to B F, B to C, G. A related to B, B related to C by transitive law. So A related to C. Similarly, F is a function from A to B, G is a function from B to C. Then there exists a function from A to C, that is GOF. GOF is a function from A to C and its inverse will be FOG, C to A. So if F is a function from A to B, G is a function from B to C, then GOF from A to C and FOG from C to A are called composite functions. Then question comes, what is the meaning of this GOF and FOG? Your GOF x equal to G of Fx, FOG x equal to F of Gx. Let us see with an example. Suppose Fx equals to x square plus 1, Gx equals to sin x. Then compute GOF and FOG. GOF x equal to G of Fx, that is G of x square plus 1. In place of Fx you can write x square plus 1. G of x is defined as sin x. G of x square plus 1 will be sin of the bracket function x square plus 1. Your FOG x, f of Gx, that is f of sin x. Fx is defined as x square plus 1. That means if the term inside the bracket is x, then right hand side will be x square plus 1. So here it will be sin x whole square plus 1, that is sin square x plus 1. So mark here GOF x is not equal to FOG x. In general, GOF x is not equal to FOG x. That means our composition is not commutative. Composition of functions is not commutative. You are all acquainted with the commutative law, that is A plus B equals to B plus and AB equals to BA, like this. So let us do one problem on composition. F having elements 1, 3, 2, 4, 3, 7. G having elements 3, 2, 4, 3, 7, 1. Compute Goff and Fogg. Here F1 equal to 3, F2 equal to 4, F3 equals to 7. Similarly, G of 3 equal to 2, G of 4 equal to 3, G of 7 equals to 1. First, let us find Goff 1. Goff 1, that is G of F1, that is G of 3. Here G of 3 equals to 2. That means under the composition for Goff 1 related to 2. Similarly, Goff 2, G of F2, that is G of 4, that is 3. Goff, next is Goff 3, G of F3 equal to G of 7 equals to 1. So Goff having elements, so in the domain set, Goff has elements 1, 2, 3, that is elements of each first element of the order pairs present in F. So 1, 2, 2, 3, 3, 1. Then we will find what is your Fogg here. Fogg 3, F of G3 equal to F2, your F2 equals to 4. So under the function Fogg, 3 related to 4. Fogg 4, F of G4, that is F of 3, F3 related to 7. Fogg, next is Fogg 7, F of G7, that is G7 is 1, F of 1, F of 1 equals to 3. So Fogg having elements in the order pair form 3, 4, 4, 7 and 7, 3. Here see that Goff having elements 1, 2, 2, 3, 3, 1. Fogg having elements 3, 4, 4, 7 and 7, 3. That means Goff is not equal to Fogg. Let us consider another example. Three, 4, 4, 7. If F and G are 1, 1 functions, then Goff is 1, 1. As F and G are 1, 1, that implies Fx1 equals to Fx2, implies x1 equals to x2, gx1 equals to gx2, implies x1 equals to x2. So Goff x1 equal to Goff x2 implies g of fx1 equal to g of fx2, as gx1 equals to gx2. Similarly, g of fx1 equals to g of fx2 implies fx1 equals to fx2 with the reasoning g is 1 1. That implies x1 equal to x2 since f is 1 1. Therefore, if f and g are 1 1 functions, then also GOF is 1 1. If f and g are onto functions, then also GOF is onto. For onto function, I have told that every function of the range set has at least one preimage in the domain set. Now, as f and g are onto, that implies for every x fx there exists x, and for every gx there exists x. Now, GOF x equals to g of fx, that implies GOF is onto. Or we can prove it another way. Let y equal to fx and that implies g of y exists. Similarly, we can prove that GOF is onto. Also, GOF whole inverse equals to f inverse or g inverse. Let f is a function from a to b, g is a function from b to c. Let f of a equal to b, g of b equals to c, like this. Now, GOF whole inverse a or GOF a g of f a, that is g of b equal to c. That implies a equals to GOF whole inverse c. Similarly, f inverse o g inverse c. Come to this point, b equals to f inverse a, c equals to, g inverse c equals to b, a equals to f inverse b, a equal to f inverse b and g inverse c equals to b. So, for f inverse or g inverse c equals to f inverse g inverse c, that is f inverse b, that is your a. Here a equals to GOF whole inverse c and a equals to f inverse or g inverse c, that implies GOF whole inverse c equals to f inverse o g inverse c, that implies GOF whole inverse equals to f inverse o g inverse. About our composite functions. Next comes identity function. We are acquainted with identity cards. A function, a person who having an identity card bears his own photograph. Similarly, a function f from a set onto itself. F is a function from a to a is called an identity function if every element of A is its own image and pre-image. That means 1 related to 1, 2 related to 2, 3 related to 3. If there is an alternation of between these correspondence, then the function is not an identity function. A function from a set A to itself is called an identity function if every element is its own image and pre-image. Also, the notation is like this: IA identity function on A. If g of x equals to fog x equals to x, then fx and gx are inverse of each other. For the finding of inverse functions, we also use the condition g of x equal fog x equal to x. In general, g of x is not equal to fog x. If it is equal, it will be there, equal to which equals to x, then fx and gx are inverse of each other. Fx equal to 2x plus 3. F is a function from R to R. Find F inverse. Let y equals to 2x plus 3. That implies 2x equals to y minus 3, x equals to y minus 3 by 2 equal to F inverse y. Let F inverse y equals to y minus 3 by 2. So F inverse x will be x minus 3 by 2. Let it be named as gx. So now we have two functions, fx equal to 2x plus 3, gx equals to x minus 3 by 2. Now we will verify whether g of x equal fog x equal to x or not. G of x, g of fx, that is g of 2x plus 3. Gx is defined as x minus 3 by 2. So g of 2x plus 3 will be 2x plus 3 minus 3 by 2, that is x. Similarly, fog x equals to f of gx equal to f of x minus 3 by 2. Your fx is defined as 2 into x plus 3. So here 2 into x minus 3 by 2 plus 3, which equals to x. So as g of x will fog x will x, so fx and gx are inverse of each other, and gx equals to x minus 3 by 2 equal to f inverse x. F inverse or f inverse of f equals to identity function I. Next comes constant function. A function f from a to b is said to be a constant function if its range set is a singleton set. You are all acquainted with the terminology singleton. Singleton set is the set having only one element. This is a constant function. Also, This is a constant function. This is a constant function. If the element C is not related to any element of set A, still then it is a constant function because its range set is A. F having elements 1A, 2A, 3A. That implies range set of F equals to singleton set A. Therefore, F is a constant function here. Next we'll come to real valued function. A function f from R to R is called a real valued function. Under this real valued function, there comes several functions. Polynomial functions. A function f from R to R defined as fx equal to a0 plus a1x plus a2x square and so on, where a0 is not equal to 0, a0, a1 and so on are real constants. p1x equal 5x plus 3 here. Degree of this polynomial is 1, so it is a linear polynomial. p2x x square plus 3x plus 8, a polynomial of degree 2, like this. So we can take also polynomial of degree n. Next comes our rational functions. F from R to R defined as fx equals to px by qx, where px and qx are functions of x and qx is not equal to 0. Px and qx are functions of x. 2x plus 3 by 3x plus 2, or x square plus 5x plus 7 by x cube plus x square plus 11, like this, all are rational functions. Trigonometric functions. A function f from R to R defined as different trigonometrical angles, fx equal to sin x, gx equal to cos x, hx equals to tan x, all are trigonometrical functions. Next comes our even and odd functions. F from R to R is said to be even if f of minus 6 will fx. Cos x, sec x, x square, x4 and so on, all even powers of x. Cosine angle and sec angle, they are sec x, cos x and sec x are even functions. If f of minus x will minus fx, then fx is an odd function. All odd powers of x, x cube, x5 and so on, sin x, cosec x, tan x, all are odd functions. If combination of these two, suppose fx will sin x plus cos x, that means sin x is odd, cos x is even, fx equal to x square plus x cube, one even term and one odd term, then fx is neither even nor odd. Suppose or fx equals to fx plus f of minus x by 2, fx equal fx minus f of minus x by 2. So this is even, this is odd. Let us add these two, fx plus f of minus x. Now f of minus x equals to f of minus x minus f of x by 2. Suppose we will add these two, fx plus f of minus x by 2, fx minus f of minus x by 2. Ultimately we have 2fx by 2, that is fx. That means every function can be expressed as a sum of an odd function and even function. That is, every function can be expressed as the sum of an even and an odd function. Suppose let fx equals to sin x, f of minus x equals to minus sin x. Now fx plus f of minus x by 2, that is sin x minus sin of minus x by 2, that is sin x plus sin x by 2, that is sin x. So here fx minus f of minus x by 2 is an odd function. Next, what about the functions, algebraic functions? F is a function from R to R which is defined with the real variable x or generated with the real variables are called algebraic functions. 3x square plus 7x plus 8. This is an algebraic function, but the functions which are not algebraic are called transcendental functions. That means all trigonometric functions, exponential functions, logarithm functions, and extraction of roots, all trigonometric functions, exponential functions, logarithm functions, and extraction of roots are transcendental functions. Next comes our modulus function. Let f is a function from R to R defined as fx equal to mod x. You are all acquainted with the absolute value or modulus of x. This is our modulus function is also called an absolute value function, where mod x equal to x if x is positive, minus x if x is negative. If you ask a general question to students what about modulus, now modulus is always positive, but it is not true. F of minus 5 equal to mod of minus 5, that is minus of minus 5 equals to 5, like this. So fx mod x represents x when x is a positive, x greater than or equal to 0, minus x if x less than 0. So graph of this modulus function is like this. Mod of 0, that is 0. Mod of minus 5 is 5, that is means it is above the x-axis. So this graph coincides or intersects at the point 0. It is symmetrical about y-axis. Symmetrical means its shape is same in both sides of y-axis. Graph of fx equal to mod x. Next comes greatest integer function. F from R to R defined as fx equal to bracket function of x or greatest integer function x, that is it is the set of integers or it is the integer, greatest integer not greater than x. That is, in general, bracket function of n x equals to n if n less than or equal to x less than n plus 1. Bracket function of 0, 0. Bracket function of 1.9, that is 1, which is the greatest integer not greater than 1.9 is 1. Minus 2.3. What is the greatest integer not greater than minus 2.3 is minus 3, like this. Also, ceiling function, it is also called floor function. Ceiling function means fx equals to like this. This is reading as ceiling function x, that is, it is the smallest integer greater than x. Suppose ceiling function of 1.9, that is 2, minus 2.3, that is minus 2, like this. Next comes our step function or jump function or post office function, like this. If a function is defined differently in different intervals, then it is called a step function or jump function or post office function. It is called post office because in postal system we have several postal charges for several weights. Therefore, it is called post office function. F from R to R is called a step function if it is defined differently in different intervals. Your best example is greatest integer function is the step function or jump function. Between 0 and 1, it will be along x-axis, 1 to 2, 1, 2 to 3, like this, minus 1 to 0, minus 2 to 1, like this. So it is just like a staircase or steps. Therefore, it is called a step function and the function is defined differently. Fx equals to 0, 0 less than equal to x less than 1, 1, 1 less than equal to x less than 2, 2, 2 less than equal to x less than 3, like this. Therefore, it is called the step function or jump function or bracket function. Next, exponential function. A function f from R to R plus is called an exponential function if it is defined as fx will be a to the power x or e to the power x. Fx will be e to the power x if a to the power x if a greater than 1. If in between a lies between 0 and 1, the graph will be like this. So, fx will be a to the power x for the condition 0 less than a less than 1. Now its properties are also if we take as fx will e to the power x where e equals to 2.718 like this, then it is also the exponential function. Properties: e to the power x plus y equal to e to the power x into e to the power y, e to the power x minus y to e to the power x divided by e to the power y, e to the power mx equals to e to the power x whole to the power m like this. Next is our logarithm function f from r plus to r. That means log x is defined only for x greater than 0, defined as fx log x base a is called the logarithm function. This is a graph of log x base a subject to a greater than 1. Log x base a 0 less than a less than 1. That means for a greater than 1 this is an increasing function, for a less than 0 less than a less than 1 it is a decreasing function. Its properties: log x base a, that is means is log x by log a, log a into b, log a plus log b, log a by b, log a minus log b, log a to the power n equal to n log a. Certo. fx equal to x cube is 1 1, f1x equals to x1 cube, f2x equals to x2 cube. Taking f1x equals to f2x implies x1 cube equals to x2 cube, implies or x1 minus x2 x1 square plus x1 x2 plus x2 square equals to 0, implies x1 minus x2 equals to 0 because this factor will not be 0, implies x1 equals to x2. So fx will x cube is an injective function or 1 1 functions. So in the next class we will discuss about other problems only. Thank you all.